Okay, this is a temperature profile, and this is important. Okay? Again, I'm going to do some drawing over here because it's a little hard to read that. Ground level here. It's tough to see this, but there's a dotted line here. And let me put that in here. And this first section of our atmosphere is called the troposphere. Right? Troposphere. So this is showing us what the temperature does as we leave Earth's surface. All right? So down here, this is zero elevation. We're down at sea level. Temperature gets colder as we go to the left. What do you see? We see this red line depicting temperature as we rise up in the troposphere. How would you describe what's going on here?
Getting colder?
It's getting colder, and it's getting colder at a very steady rate. So that's what you'd expect. Remember, the atmosphere warms from the ground up because of Earth's long-wave radiation. So the closer you are to Earth's surface, the warmer the atmosphere is going to be, and that shows that very nicely. There's a term for this, it's called the environmental lapse rate. In other words, the degree to which the temperature drops as we move up. It's a fairly steady drop. But we see something very strange happening here. Okay? So that temperature curve then in the troposphere shows a nice steady decline. And then we get up into the next section of the atmosphere we call the stratosphere.
Missing tropopause?
And yes, and the boundary is called the tropopause. That dotted line, tropopause. Okay, what we see though, the temperature's not doing what I said it does. We see a temperature that levels and then actually increases in the stratosphere. Okay? There's something very important going on here. Now, normally, like I say, the atmosphere is heated from the ground up. Something is going on here, and what it is, it's a concentration of a gas called ozone, and its formula is O3. Okay? Ozone. Now, what is ozone? Well, it's just 3 oxygens bonded together. Down here, we have a lot of O2, but we also have some O2 up here. Now, O2 is what we're breathing right now. O2 is simply 2 oxygens bonded together, 2 oxygens bonded together, sharing 2 electrons in their outermost shell. When you see the O2, they're always together. It's called a diatomic molecule because they're sharing 2 electrons. All right? Now, O2, let's go further up here. Our O2s, some of our O2 does get up into the stratosphere. But as this incoming shortwave solar radiation comes in, there's one part of that shortwave solar radiation called ultraviolet light that can split that bond. So O2 up there can go to O plus O, single oxygens. So now we've got some single oxygens kicking around here in the stratosphere. What can happen then? They can combine with some of the O2 to produce ozone at O3. Now, the thing to take from this, ozone is not a very stable molecule. It's easily broken up. So we constantly see the breaking up of ozone, but the remaking of it, okay? That's what keeps that ozone replenished up there. Now, what is the ozone doing? The ozone, the O3 here, when the UV light comes in, it absorbs it. That's the characteristic of ozone. It absorbs ultraviolet light. When it absorbs it, it heats up. That's why it's showing a temperature increase in the stratosphere. So we're seeing a heating up of the ozone as it absorbs that ultraviolet light. That's really good news for us, because if ultraviolet light penetrated to the surface, we would not be here today. We'd be long gone. We'd be dead. Ultraviolet light will kill you. It will kill plants. It will kill animals. Now, some of the bad news regarding this. Well, actually, before we get to the bad news, let's continue on with this. Once we leave the stratosphere and leave this ozone layer, temperature decreases again. just like we would expect it to do. That's in the mesosphere, okay? We're not going to talk about the thermosphere. It's a theoretical sort of thing going on. Very few molecules up there. Look at the pressure, 0.001 millibars. There's hardly any pressure there anyway. So just to review, to summarize, temperature decreases steadily through the troposphere. It then increases in the stratosphere because the ozone, the O3, absorbing ultraviolet light and heating up. Then when we get up to the mesosphere, temperature declines again. Now, I want to tell you that we discovered this ozone hole back in the late 70s, around 1980. We finally had the capability of putting a satellite up to measure the amount of ozone. And what we found, starting around 1980, there was a complete lack of ozone over parts of the South Pole. And then look at the progression through the 80s. That ozone hole got larger and larger, all right? This is a serious thing, because remember, ozone protects us from ultraviolet light. Ultraviolet light will kill any life on the planet. So a lot of people started doing some research on why would this be? Why are we losing ozone? Why is the ozone being eliminated from the South Pole? And it was discovered that a particular type of chemical we were using here on the planet, and the acronym is CFC, or CFCs, plural. That stands for chlorofluorocarbon. So chlorofluorocarbons. And they were used in things like refrigerants, propellants, stuff like that back in the 60s and 70s. But what we found was these CFCs could work their way up into this O3 layer, the ozone layer. The CFCs combine with the ozone to break it down. And this would be plus O for them to balance it. So it was believed that chlorofluorocarbons use was breaking down the ozone layer. So in a very remarkable treaty that I've never seen another one like this around the planet, in 1987, over 100 countries on the planet signed the Montreal Protocol. So that would be 1987, to reduce and then eliminate the use of chlorofluorocarbons on the planet so that we could stop, prevent, mitigate, whatever you want to call it, this ozone hole. So that's the good news. I mean, this is trotted out as a remarkable thing that happened in terms of the planet agreeing on something. When was the last time when all our countries agreed on something, right? So that's the good news. You want to hear the bad news? Hasn't affected anything. The Montreal Protocol was signed in 1987, and we fast forward today, 2013, the ozone hole is still just as big as it ever was. What does that tell you? We were successful at preventing CFC, we stopped the use of CFCs pretty much. So why is that hole not getting smaller? What we're thinking now, it's not just CFC. And there's more research going on right now into things like nitrogen oxides. We're starting to think, other chemicals are doing this. So, that's the bad news, that we have the technological capability to put ozone up there ourselves. So maybe that's what we're going to start. I mean, that's a pretty big task. It's a pretty big planet. But we do have a lot of B-52s. And I'm picking on them because we have a huge fleet of Boeing B-52s sitting around doing nothing. Let's put them to use. We're also seeing a bit of a thinning over the Arctic. We're seeing a bit of thinning over, I think I got one slide up here, over Canada. The further north and the further south you go, the more ozone thinning we're seeing. So over Canada, on average, we're seeing about a 6% decline in the ozone since the late 70s. So it's not just a South Polar Antarctic situation, right? Now, I wouldn't get too excited about a 6% loss. I think the thing we want to watch is it going to continue? Are we going to continue to lose ozone over Canada? There's very little ozone loss over the United States. The further south we get, the less we see. It's almost negligible down here. It's a non-issue really in the United States right now. It's a bit of an issue in Canada because you can see that up in the high Arctic, we've seen losses up to 45% of the ozone in northern Canada. So it has been an issue, and don't know. It's just something we got to continue monitoring.